Welcome to G Fun Facts Online. In the silent, black expanse of space, humanity's most powerful eye, the James Webb Space Telescope, has turned science fiction into scientific fact. Astronomers have just created the first ever three-dimensional map of the weather on a world hundreds of light years away. This isn't just a technical victory, it's a giant leap in our quest to understand the countless worlds in our galaxy and, perhaps one day, find one that looks like home. The subject of this revolutionary study is a planet called WASP-18b, a colossal gas giant that redefines the word extreme. For decades, finding planets outside our solar system, or exoplanets, has been a game of shadows. These worlds are so distant and faint, lost in the blinding glare of their parent stars, that we've had to rely on indirect tricks to even know they exist. We could spot the tiny dip in a star's light as a planet passed in front of it, a method called transit photometry. Or we could detect the slight wobble in a star's position caused by the gravitational pull of an orbiting planet. These methods were brilliant, revealing thousands of exoplanets and giving us basic stats like their size, mass, and how long their year is. But the most interesting part, the atmosphere, the very key to a planet's climate and potential for life, remained a frustrating mystery. We were looking at these worlds in one dimension. Early telescopes like Hubble and Spitzer gave us tantalizing clues, detecting molecules like water or carbon monoxide. But it was like taking the average temperature of Earth by mushing the poles and the equator together. It gives you a number, but it doesn't tell you about the weather. The James Webb Space Telescope has completely changed the game. With its enormous gold-plated mirror and hypersensitive instruments, it can capture the feeble light from these alien worlds with a clarity we could only dream of before. This power allows us to move beyond just saying a planet is there and start asking, what is it like there? We can finally start to characterize their atmospheres in 3 dimensions. Let's talk about the target, WASP-18b. This planet is nothing like anything in our solar system. It's located about 400 light-years away and belongs to a class of exoplanets called ultra-hot Jupiters. As the name suggests, they are gas giants, but they orbit their stars at terrifyingly close distances. WASP-18b completes a full orbit, its entire year, in just 23 hours. Imagine your birthday coming around every single day. This extreme proximity means it gets blasted with radiation, making it one of the hottest, most intense environments we've ever observed. It's a true monster, about 10 times more massive than our own Jupiter. And because it's so close to its star, it's tidally locked. This means the same side of the planet permanently faces the star, resulting in a permanent, scorching hot day side and a permanent, frigid night side. This massive temperature difference is the engine for some truly wild atmospheric dynamics. Even before Webb, we knew WASP-18b was weird. In 2017, observations suggested its atmosphere was full of carbon monoxide but had a mysterious lack of water, which was a puzzle because water is a very common molecule in the universe. So, how did Webb create a 3D weather map of this bizarre world? The technique is as clever as it is complex. It's called spectroscopic eclipse mapping. It works by observing the planet during a secondary eclipse, which is when the planet passes behind its star from our point of view. As WASP-18b begins to slide behind its star, the total light we see from the system, star plus planet, starts to dim. First, the edge of the planet's day side disappears, then the middle, then the other edge. By precisely measuring this decrease in light, astronomers can calculate the brightness and temperature of each slice of the planet's atmosphere as it gets sequentially blocked from view. But the real magic comes from spectroscopy. Webb's instruments can split the incoming light into its component wavelengths, like a prism creating a rainbow. Different molecules in an atmosphere absorb light at very specific wavelengths. Water, for example, is a strong absorber of certain types of infrared light. By watching the secondary eclipse across a whole range of these wavelengths, astronomers can probe different depths of the atmosphere. At wavelengths where water absorbs a lot of light, they're essentially seeing the upper layers. At wavelengths where the atmosphere is more transparent, they can see deeper down. By putting all these observations together, the dimming light over time, combined with the data from multiple wavelengths, they can build a complete three-dimensional picture of the planet's temperature, varying with latitude, longitude, and altitude. This is incredibly difficult. The light from the planet itself is less than 1% of the light from its star. As Ryan Challoner, the lead author of the study, explained, "You're looking for tiny changes in tiny portions of light as the planet disappears." It's an extraordinary challenge, but the results are breathtaking. The 3D map reveals a world of fire and fury. The day side of WASP-18b, forever facing its star, is a cauldron heated to nearly 5,000 degrees Fahrenheit, or about 760 degrees Celsius. That's hot enough to melt rock. The map clearly shows a hotspot, the very point on the planet directly beneath the star. Interestingly, this hotspot is very concentrated. This suggests that the planet's winds aren't very efficient at spreading that immense heat around. Unlike Jupiter in our solar system with its planet-spanning jet streams, the energy on WASP-18b seems to stay put, creating an incredible temperature gradient across the surface. But the most stunning discovery confirmed a long-held theory. The data showed that at this scorching hotspot, the temperature is so extreme that it's literally tearing water molecules apart. This process is called thermal dissociation. The H2O molecules are broken down into their constituent hydrogen and oxygen atoms. It's a chemical process driven by pure, raw heat. Scientists had predicted this could happen on such extreme planets, but to actually see the chemical signature of it in real data is a landmark moment. This finding also solves the old puzzle of the missing water. While the hottest part of the planet is destroying water, Webb's sensitive instruments did detect the clear signature of water vapor in the cooler regions of the atmosphere, closer to the edge of the day side and on the night side. This highlights why 3D mapping is so revolutionary. A planet-wide average would have missed this nuance, but by mapping the composition across the globe, we get a much truer, more complex picture. So what does all this mean for the bigger picture? This achievement marks the dawn of a new field, comparative exoplanetology. For centuries, we've compared Mars to Venus to Earth to understand how planets form and evolve. Now, we can start to do the same for worlds orbiting other stars. There are hundreds of other hot Jupiters out there. By applying this same technique to them, we can start to see patterns. Do they all have hotspots that destroy water? How do their winds and weather change based on their mass, their rotation, or the type of star they orbit? These are the questions we can finally start to answer. And while WASP-18b is far from habitable, these techniques are a critical stepping stone in the search for life. The ultimate goal is to find an Earth-like planet and scan its atmosphere for signs of biology. The ability to create 3D maps will be essential. It could help us identify climate zones on other worlds, like a potentially habitable terminator zone on a tidally locked planet, a permanent twilight ring where temperatures might be just right for liquid water. More importantly, understanding the complex chemistry of alien atmospheres is crucial for interpreting potential biosignatures. If we detect oxygen on a distant world, we need to be sure it's from life and not from some non-biological chemical process, like water being split apart by starlight. 3D mapping provides that deeper level of chemical and physical context. The mapping of WASP-18b is just the beginning. The James Webb Space Telescope will continue to peel back the layers of these alien worlds, building a catalog of distant skies, each with its own unique weather. Each new map is another step on a journey driven by one of humanity's oldest questions. As we continue to gaze out into the cosmos with these new, powerful eyes, we move closer and closer to finding out if we are, after all, alone in the universe. Thanks for tuning in to G Fun Facts Online.